Hello all and welcome to this video. So I want to congratulate you so far for making it to this point, because so far we've got done with some basic concepts such as current, voltage, and power, and analyzing some basic circuits and elements and the power that they dissipate or absorb or supply. So in this portion we want to talk about some basic laws that will help us ultimately to be able to analyze more complex circuits. So the first thing is Ohm's law. We want to look at relationship between current, voltage, and resistance. Then the nodes, branches, loops in circuits. Kirchhoff's current law, KCL. Kirchhoff's voltage law, KVL. Current division, voltage division, and Y delta transformations and delta to Y transformations. So let's start right off here with Ohm's law. You may have heard this before and you might be familiar with this, but the idea behind it is that every material has some property called resistance, and that resistance is composed of the intrinsic property of the material resistivity, which is rho. And this depends, for example, on the material. So silver has a much lower resistivity than glass, for example, and the relationship that was found in the laboratory was the following. Resistance is proportional to the length of the material. So as the length increases, the resistance also increases. Resistance is also inversely proportional to the area. So as the area increases, the resistance decreases. And if you put this into equation, what you get is some constant times the length over the area. And that constant, you can find this, it's an experimental method, you can find it, and they found it to be resistivity. And what you end up getting is resistance is the resistivity over multiplied by length over area. And we got to distinguish between resistivity and resistance. Resistivity is some intrinsic property of the material, whereas the resistance changes depending on the length and the area. So there's a difference there. So that's the first point there. That's the physical, like a physics method of looking at it. Then the other issue is we got to think about Ohm's law, which states that the voltage across the resistor is proportional to the current flowing through it. So what that means is, if you apply some voltage across some material, it's going to be proportional to the current running through the material. So if you increase the voltage, the current's going to increase also. And that constant of proportionality that Mr. Ohm found, Simon Ohm, was the resistance. That's the constant of proportionality. So that is Ohm's law right there. And the idea is that the resistance is the ability for a material to resist the flow of an electric current, which is going to be V over I. And the ratio of these two will tell you what that resistance is. So if you have a very high voltage and a very small current, that makes sense that there was a high resistance where you had to apply more and more of a voltage to get a small current flowing. And if you have a very high current and a very low voltage, that means that you have a material that doesn't have much of a resistance. So with a little bit of a voltage, you got a huge current. Okay, let's now talk about two important cases in circuit analysis that we should all be familiar with. One is this case. Let's draw excuse me, let's draw two components with two terminals. Alright, so in the first case, let's assume that, let's draw a wire. Yeah, plus, and this is some black box. There's some devices inside of it that we don't know. We just simply put a wire across it, a wire that we assume has resistance of 0, which of course is not very, in the real world, materials always have some resistance to them, except for superconductors, which we won't get into here. But the resistance of this wire, we can approximate all wires to have a resistance of 0 in this class. So when that is the case, if you apply Ohm's law, we get I times 0 resistance, which is 0. So that means that the voltage drop across the component is going to be 0. So there's some current flowing through, and the current could be anything, but the voltage drop, since the resistance is 0, the current's going to be the same, and the voltage is not going to be dropping at all. So that's one thing to remember. And you always want to watch out for short circuits, because you can damage, you can have high currents flowing through a wire, and you can heat up that wire, and you could damage components. So you always want to watch out and make sure you don't get short circuits. The only reason we use short circuits is in theory, where we assume that wires have 0 resistance, and we simply do it for simplifying the math. But in the real world, you should never really, unless otherwise specified by an instructor, you should never be putting wires across terminals, especially if they're high voltages. You should not be doing that. Okay, so that is called, then what this is called a short circuit, as we said. And we need to remember the properties of a short circuit. What it is that the same current that was coming here is going to be flowing there, and the voltage drop across the wire is 0. Across the short circuit, the voltage drop is 0. So we need to remember this, and that R is equal to 0. So that's the important part to remember there for short circuits. The other situation is when you have another black box. Let's remember that let's call these black boxes. Something's going on inside that we don't know what it is, but once we connect a wire across the terminals, which again, you should not do this in the real world. You should not just simply connect wires in a laboratory across some load, because you do not know the voltage current relationship inside, and you may have a very high current rushing out and burning something up or damaging components. You should not be doing what we typically do is we actually just when we absolutely don't know anything about the black box, what's going on inside, what you would do is connect some high resistance just to be safe. For example, let's see, some reasonable value would probably be 10K or so. You put it or 10,000 ohm resistor maybe, and see what the voltage drop across of it is, and use Ohm's law and see what the current is through it, and using that and a few other resistors, you can see the response of this system to the voltage and current or the resistance that you put in, and that way you can predict what kind of currents and voltages you'll be dealing with. Whereas if you just simply put a or almost 0 resistance in the real world, you gotta remember there's some resistance to all materials. So this might be, for example, half an ohm or an ohm or something like that. And if you put that across there, you're gonna get a real high current, and that would be damaging to your components, and it could be dangerous to your own life. So do not do this in the real world. Only in theory we'll do this to make the math simpler. In the other scenario, we again have a black box, and what we want to do is have a wire here and another wire here, and have an open circuit. It's called an open circuit. And what's going to happen here is you have some voltage across it as before. Voltage, positive sign, negative sign, so that's the polarity of the voltage. And you have some current flowing, or in this case, I'm going to draw it this way, but there's no current flowing, because what's going to happen here when you have an air gap like that, when the connection is broken, you have resistance approaching 0 or equaling 0, approaching infinity, and that is an approximation because what's going to happen is when you have a wire here and a wire here, you would need voltage to approach infinity to ionize the air molecules to produce a conductive path for the current to flow, which is what happens when you have lightning. You have very, very high voltages produced by very high and strong electric fields that ionize the air molecules. They pull out the electrons, and that allows a conductive path. So when you have an open circuit like this, we say that resistance is approaching or is equal to infinity. Therefore, when that is the case, if you look at Ohm's law, well, V is equal to IR, and if I rearrange to solve for I get V over R. Now if I take the limit as R approaches infinity on both sides, which is a calculus property there, so as R approaches infinity, what you're going to get is that the current is equal to 0. So no current is going to flow. Therefore, and that makes sense because we already said for the current to flow, current takes the path of least resistance, which in this case it has nowhere to go, and the resistance here is almost infinite, or it's so huge that we just say infinity in terms of engineering. So no current's going to flow, and you're going to see the full voltage, whatever the voltage was before here, you're going to see the whole thing across here. So the open circuit voltage. Open circuit. Voltage sub open circuit. So the characteristics to remember about an open circuit is that the resistance is almost infinity or approaching infinity, and that the current is 0, and that the voltage is going to be, you're going to read the same. For example, let me write it like this. Let me give you an example here so it makes more sense. If you have some voltage source, and let's see here, let's take the resistor out for now, and if you have an open circuit like this, and let's say this is 30 volts, what you're going to get here is, if you put your probe here and try to measure this, you're going to read 30 volts. That is the open circuit voltage. And for example, if I put a resistor here, current's going to want to go to the path of least resistance, so it's not going to want to go here because the resistance is almost infinity. But let's say this is like let's say this is 10 ohms. So you're going to have 30 volts across here, and you'll have some current flowing, which is 30 volts over 10 ohms, which is 3 amps. You'll have 3 amps flowing here, which is a pretty big current. And just to give you kind of a idea of how much that is, as a rule of thumb, currents of, let's write it like this, currents of 250 milliamps and higher can really do some damage. They can be lethal and stop your heart. So that tells you 3 amps can be, what is that? That is 4 and about 12 times more dangerous than a 250 milliamp current. So that kind of gives you a perspective there. And what's going to happen is that the current's going to flow here, and we're still going to read the same voltage of 30 volts across this element and this the open circuit. So that's one example there. And let's see, let's do another example then. Let's say now we have 20 volts and you have some resistor here, and then again open circuit. So I want you to pause the video and think about what's going to happen here. Let me get 20 ohms. What's going to happen here if I bring a voltmeter, the positive probe, put it here, and the ground probe or the negative probe, put it here. What is going to be the reading here for the voltage across this open circuit? I want you to pause the video and think about it. Okay, I'm assuming you've tried to answer this. So what's going to happen is, if you think about it, applying Ohm's law, V is equal to IR, to determine the current flowing here, I'm going to say I is equal to V over R. And you got to remember, resistors in series add. So we can imagine that this whole thing, that we know that the air gap has a resistance of infinity almost, or it's approaching that. So if we say that the resistance equivalent, or the resistance of this whole circuit, when we add up infinity and 20, it's going to be, infinity is so huge that you don't even have to worry about that 20 ohm. It's so small compared to that. So we'll just say infinity. So what's going to happen here then again is that the current is going to be the voltage 20 volts across over infinity, which if you take a limit, you get a current of 0. And that makes sense mathematically, as I just demonstrated. And also in a physics perspective, it also makes sense, because if you have, let's draw something here. Let's say you have that mountain one more time. You have some mountain, and you have water flowing from the top of the mountain from a higher potential to a lower potential, gravitational potential that is, and you have some straw or some pipe that's going like that, and you have the water flowing through that pipe like so. And let's say, and yeah, we're going to assume that the pipe is bound very tightly to the mountain so it's not falling out. Let's call the diameter D, and let's assign this rule that if D, let's say right now it is at, I don't know, 5 meters. Let's just assume that for now. If D is greater than 5 meters, what's going to happen? If you have a greater diameter, there's going to be a less resistance to the flow of water, right? So if D is greater, then you're going to have more water flowing through. So I'll call this I, just to draw a better analog to the current. So let's write it over here. So if D is greater than 5, or I can just say if D increases, we can just say if D increases, just symbolically, since it isn't just a conceptual example, we don't need to be very rigorous here. So if D increases here, you're going to have more current flowing there. And if D decreases, meaning if it gets smaller or narrower and narrower, you're going to have less current flowing, which makes sense, right? So let's take a limit. For example, let's limit as D approaches 0. What's going to happen as the diameter of this pipe approaches 0? Well, let's see, I don't really have a function to take a limit of, but just conceptually though, if you take a limit of that, you'll get, I guess I can just say current, because current in this case is a function of the diameter. So I can write that and then say, what's going to happen here is that as you take the limit of D approaching 0, you're going to get a current of 0. Meaning, you can imagine if the pipe first decreases into the size of a straw, and then decreases and decreases, well, no water is going to be flowing through a straw which is ever so decreasing to where the D is, where the diameter is almost 0. So that makes sense in that type of perspective. So in this case, when the diameter is decreasing, resistance is increasing. So when D approaches 0, we can say that the resistance to the flow of water is approaching infinity, which is similar to this case. So you're going to have no current flowing. So that is that example. So before I end this video, I want to real quick talk about resistance and some of the resistors that you'll encounter. So what we're going to assume in this class is that the resistors that we encounter are going to be linear, meaning the voltage and current relationship that they have when applied, when you apply a voltage across it, like so, you'll get a current going through it from a high potential to a low potential this way. And let me not forget the voltage, plus minus volts there. And the behavior then, if you use a graph for it, you'll get, let's see, let's wait, draw a better one. You have current versus voltage. What you get is a curve that is linear under certain conditions. And that condition, and that is the slope. The slope is going to be, if you remember, V equals IR. So V over I is going to be R. So the slope of the voltage over current is going to be the resistance. And what we got to remember though is that in this approximation, in this class, we're going to be saying that all the resistors that we deal with are going to be linear. But in the real world though, there are resistors that are called nonlinear resistors, which will look something like this. Their voltage current characteristic is going to look something like this. Going to be could just be a curve. Which one example would be, for example, a light bulb, which the resistance varies depending on the temperature, and again, slope is going to be the resistance. Which you can see, we cannot simply apply Ohm's law because of the different slopes that we have here, and it's not a linear relationship. So the current, the voltage depends on the current in a non-linear way in this case. So we need a function. So in this case, it might be a cubic function or some other approximation like that. So we can't simply use Ohm's law here. Ohm's law does not apply here. And that's another key point to point out. It is that Ohm's law is not a physical law like F is equal to ma. It is simply an approximation that we can apply when we assume that the resistor is in a certain temperature range where the thermal excitations do not affect the resistance of the actual resistor. That's one thing to remember. Another thing is, another key point about resistors is that they come in generally they come in two varieties. So you have a fixed resistor, which for example can have a value of like this one, for example, is called R1, could be like 100 ohms, for example. But then you have another kind of resistor, which is a potentiometer, and what it does is it gives you an ability to control the resistance across the terminal, and it's shown by drawing an arrow across the resistor like that. And that arrow usually means a variable, meaning it's not constant, you can vary it. And it can be useful in tuning instruments and things like that. So basically what's going to happen is you can vary the resistance, for example, between 10 ohms and, I don't know, 500 ohms. And with doing that, you're going to control obviously the voltage drop across the resistor and the current through the resistor, which can be useful in some applications. And another thing to remember about resistors is that nowadays they're either surface mounted, for example in the, you can look that up on Google if you're interested. Surface mounted meaning with, for example, digital circuits and very small miniaturized kind of circuits. Or it could be integrated, and I can give you guys some examples, or you can look it on Google. And that is pretty much the basics that we need to cover about this before we go on to analyze more complex circuits and look at the basic laws that we're going to be talking about. Thank you guys, and I'll see you in the next video.